Welcome back to Mr. Vaughn's classroom. Before we get started, I'd like to ask you to please hit the subscribe button, give this video a thumbs up, and be sure to leave a comment below and let me know if there's any help that I can offer you. Today, we're looking at Unit 5, Introduction to Exponential Functions, Lesson 17, Different Compounding Intervals. The learning goal today is to find out what happens when we repeatedly apply the same percent increase at different intervals of time. We have two learning targets today. You'll want to think about these as we work through the practice problems, and at the end of the lesson, we'll come back and review them to make sure you understand everything you need to so that you're set up for success moving on to future lessons. Learning target number 1 says I can calculate interest when I know the starting balance, interest rate, and compounding intervals. Learning target number 2 says when given interest rates and compounding intervals, I can choose the better investment option. Now we can begin the practice problems for Unit 5, Lesson 17, Different Compounding Intervals. The population of a city in 2010 is 50,000, and it grows by 5% each year after. Number 1, write a function f which models the population of the city t years after 2010. So, a couple of things that you need to know ahead of time. If we multiply by 1, then it stays the same. If we want to grow by 5%, then first we need to understand that 5% equals 0.05. You take the decimal point and you move it 2 spots to the left. So if I want to grow by 5%, then I need to have the 1, which makes the population stay the same, and then the 0.05, which increases that population by 5%. So now on number 1, we can write the equation. We're going to call the function f, and we're going to use t as the input. So we would say f of t equals the initial amount, 50,000, times the growth factor, which is going to be this 1.05, to the power of the input, which is going to be t, to represent the number of years after 2010. So this would be the exponential function that would represent a population of 50,000 growing by 5% each year. Number 2, what is the population of the city in 2017? Well, 2017 is going to be 7 years after 2010. So we want to say f of 7 equals 50,000, which is the original population, times that growth factor of 1.05. The 1 maintains the population, while the 0.05 grows it by 5%. And now our exponent is going to be 7. And now we can put this in a calculator. 1.05. We want to use this button that says x to the power of y. That way it'll let us type in the power that we want. And we want that exponent to be 7. And we get this 1.4. Now we're going to multiply that by the 50,000 original population. And because we're talking about people, we're going to want to round it to the nearest whole number. So 70,355 people. Number 3 has 2 parts. First, what will the population of the city be in 2020? And then, what will the population be in 2030? So first, if we're talking about 2020, then that is 10 years after 2010. So we're going to have f of 10 equals that original population of 50,000 times the growth factor of 1.05, which maintains the current population and grows it by 5%, and our exponent is going to be 10. We can go to the calculator, and we have 1.05 to the power of 10, and we get about 1.6. So we're going to multiply that by the original population of 50,000. Again, we're talking about people, so we want to round to the nearest whole number. So we would say the population is 81,445. Next, they also want to know about 2030. 2030 is going to be 20 years after 2010. So we would say f of 20 equals that original population of 50,000 times the growth factor of 1.05, which maintains the current population and grows it by 5% each year. And now our exponent is going to be 20. So we go to the calculator. 1.05 to the power of 20 gives us approximately 2.7. We multiply that by the original population of 50,000. And we want to round to the nearest whole number because we're talking about people. So this is 132,665. And number 4, by what factor does the population grow between 2010 and 2020, then what about between 2020 and 2030? So what we're going to do is we're going to take the second population and we're going to divide it by the first population. So in 2020, that was the f of 10. So we would say 81,445 people divided by 2010 was the original population of 50,000. We put that into a calculator. 81,445 people divided by 50,000 people gives us a growth factor of approximately 1.6. Now, between 2020 and 2030, we're going to do the same thing. 2030 was the f of 20, and we said that was 132,665 people. And in 2020, we said the population was 81,445 people. We put this into a calculator. 132,665 divided by 81,445, and we get approximately 1.6. So notice the same 10-year time, and we had the same factor, 1.6. So every 10 years, this population is growing by approximately a factor of 1.6. If you have any questions about how to solve this practice problem, please leave a comment below and I'll get back to you with any assistance I can offer. Our next practice problem says a person charges $100 to a credit card with a 24% nominal annual interest rate. Assuming no other charges or payments are made, find the balance on the card in dollars after 1 year if the interest is calculated, number 1, annually, number 2, every 6 months, number 3, every 3 months, number 4, monthly, and number 5, daily. So there might be some terms here that I need to help you understand. When we say 24% nominal annual interest rate, this means total interest rate for the year. So when we look on the right, if we charge annually, then that means one time. So the exponent would be 1. If they charge every 6 months, then that's going to be 2 times. And we're going to say 12% each time so that we have the 24%. Number 3, If they're charging every 3 months, then that's going to be 4 times, and each time will be 6%. So that you have your total of 24% for the year. Monthly, this means we would charge 12 times, and each time would be 2%, so that we would have that 24%. And if we did it daily, that would be 365 times, and each time would be 24% divided by 365 days. So now what we'll do is each time we figure this out, we're going to have the same initial starting value, $100. But each time is going to have a new growth factor, and it's going to have a new exponent. So for number 1, we can say y equals the $100 we start with times the growth factor. Well, if it's 24%, we move that decimal point 2 spots to the left. We maintain the 1 to keep the current value, and then have the 0.24 to represent the 24%, and the exponent is once, because we're charging annually, so we're charging 1 time. So anything to the power of 1 is just itself. So we have 1.24 times the $100 we started with. So we would owe $124 on the credit card. That's if they charged interest once a year. Now we can look at number 2. We start with that same $100. This time, we're going to do it every 6 months, so that's twice a year at 12% each time. So this time the growth factor would be 1.12, because the 1 is going to maintain the current amount, and the 0.12 is going to represent the 12% in interest each time. And because we're doing this twice, once every 6 months, the exponent is going to be 2. So we're going to go to the calculator. 1.12 to the power of 2. And now we're going to multiply that by the initial $100. Now you can see that we would pay $125.44. And so even though this credit card claims to have a 24% interest rate, just by having you pay 2 times a year instead of once, they can make an extra $1.44 off of you. Now we can look at number 3. Y equals the original 100. This time the growth factor, because we're doing it every 3 months, that means we're going to charge 6% 4 times to make that 24% annual interest. So 1.06, the 1 maintains the current amount. The 0.06 represents the 6% interest. And the exponent is now going to be 4 because we are charging interest 4 times per year. So we go to the calculator, and 1.06 to the power of 4, and then we multiply this by the original $100. We round to 2 decimal places because we are talking about money, and the 7 tells us to round that 4 up to a 5. So we pay a total of $126.25. And now notice, the credit card company is allowed to claim that it's still just a 24% nominal annual interest rate, but by charging you interest 4 times per year instead of 1 time per year, they have now made an extra $2.25 off of you. Number 4. Y equals the original $100. This time the growth factor is going to be 2%, and it's going to happen 12 times. So 1.02, the 1 represents the current amount, and the 0.02 represents the 2% interest. And the exponent becomes 12, because if we're charging interest monthly, we're going to charge it 12 times. We go to the calculator, 1.02 to the power of 12, and then we multiply that by the original $100. We round to 2 decimal places because we're talking about money, and the 4 tells us to leave the 2 alone. So we would pay $126.82. So now you can see, even though the credit card is allowed to claim the same interest rate, by charging you monthly instead of charging you yearly, they have made an extra $2.82 off of you. And now with our last one, number 5, Y equals the initial $100 times, we would be taking the 24% interest rate and we would be dividing it by 365 because there's 365 days in the year. So in a calculator, we would say 24 divided by 365. And we have this really long decimal point. We're going to go ahead and add the 1 to maintain So this is representing percentage. I need to turn that into a decimal. So I'm going to move the decimal point 2 more spots to the left. So divide it by 100. And we're going to add 1 to maintain the current amount. So now we can see that this would be 1.000657. So we could say 1.000, and this 5 would round this 6 up to a 7. And because we are doing this daily, then the exponent is going to be 365. So I'm going to leave this in the calculator because I don't want to round until my final answer. So I'm going to take this amount. The 1 is maintaining the current amount. This big decimal point here is representing the 24% divided by the 365 days. Now we're going to take this to the power of 365, since we are doing this 365 times. And now we're going to multiply that by the $100 we started with. Now that we have our final answer, this is where we can round. Because we're talking about money, we want to round to 2 decimal places. So the 4 tells us to leave the 1 alone. So we would pay $127.11. So here we can see that even though a credit card company would be allowed to claim this 24% nominal annual interest rate, by having you pay the interest more often, you actually end up paying more money. So if they just charged once per year, then you would owe them $124. But usually a credit card company charges you monthly. That would make them an extra $2.82. And if they did it daily, they would actually make an extra $3.11 off of you. So this is how nominal annual interest rate works. You still have a 24% that you are dividing by the number of times that you're going to charge it. You change your exponent to show how many times you're charging it, and then you multiply it by the original amount. If you have any questions about how to solve this practice problem, please leave a comment below, and I'll get back to you with any assistance I can offer. Our next practice problem says a couple has $5,000 to invest and has to choose between 3 investment options. Option A is a 2.25% interest applied each quarter. Option B is a 3% interest applied every 4 months. And option C is a 4.5% interest applied twice each year. If they plan on no deposits and no withdrawals for 5 years, which option will give them the largest balance after 5 years? Use a mathematical model for each option to explain your choice. So let's look at option A. We would begin with the $5,000. We would be multiplying by a 2.25% interest. So that would be a growth factor of 1.0225. The 1 maintains the current balance, and the 0.0225 represents 2.25%. Now, this is going to be applied each quarter. So that means it's going to happen 4 times per year. But we see that this is going to be for 5 years. So we're going to multiply that 4 times per year times 5 years for a total of 20 times. So the exponent here is going to be 20. Now we can put this into a calculator, and we have 1.0225 to the power of 20, and then we multiply that by the original amount of $5,000. And this says that after 5 years, they would have $7,802. Because we're talking about money, we need to stop at 2 decimal places. So this 6 tells us to round the 4 up to a 5. So $7,802.55. Now we can look at option B. We would still start with the same $5,000. Now our growth rate is going to be 3%. So that is a growth factor of 1.03. The 1 maintains the current balance, and the 0.03 represents the 3% interest. If this is applied every 4 months, that means it's going to be 3 times per year times the 5 years, which would be 15 times. So our exponent is going to be 15. So this time we do have a bigger growth factor, but we have a smaller exponent. So it's not happening as many times. So now we can put this in the calculator. 1.03 to the power of 15, and we get about 1.6. Now we're going to multiply this by the original amount of $5,000. That's $7,789. And because we're talking about money, we want to stop at 2 decimal places. So the 7 tells us to round the 3 up to a 4. So that's 84 cents. So notice, even though they would be getting a larger interest, because it wouldn't be happening as often, they would not earn as much money from Plan B. Now we can look at option C. We would still start with the same $5,000. This time, we're getting the largest interest rate of any of them, 4.5%. So the 1 maintains the current amount, and 0.045 represents 4.5%. This is being applied twice each year, so that's 2 times per year, times 5 years, for a total of 10 times. So our exponent is going to be 10. We go into the calculator. 1.045 to the power of 10 equals approximately 1.6. We multiply this by the original $5,000, and we see that they would make $7,764. And because it's money, we want to stop at 2 decimal places. The 7 tells us to round the 4 up to a 5, so that would be 85 cents. So if we wanted to see which one they should choose, they should choose option A, because it makes them the most money. And this is a real-world example of why understanding math is so important. If you just looked at the interest rate, then you would not make as much money as someone else. So if this couple had simply looked at the interest rate and chosen option C, they would have made about $38 less than if they understood how to compute the interest and notice that A, even though it has the lowest interest rate, it gets applied the most times and therefore ends up having the largest return on their investment. If you have any questions about how to solve this practice problem, please leave a comment below and I'll get back to you with any help I can offer. Our next practice problem, Elena says that 6% interest applied semi-annually is the same as 1% interest applied every month. She reasons they are the same because they are both a 12% nominal annual interest rate. Number one, is Elena correct that these two situations both offer a 12% nominal annual interest rate? So, for number one, nominal annual interest equals the interest rate times the number of applications. So in this case, 6% times semi-annually, which means 2 times, equals 12%. The other one is 1% applied every month, means 12 applications. So that equals 12%. So the answer would be yes. Both offer a 12% nominal annual interest rate. Now, number two asks us, is Elena correct that the two situations pay the same amount of interest? This is where there's a difference between nominal annual interest rate and actual interest rate. Because if I have 6% 2 times per year, then my growth factor is going to be 1.06. The 1 maintains the current amount, and the 0.06 represents the 6% interest, and my exponent is going to be 2. So if I put this into a calculator, 1.06 squared equals 1.1236. So it would actually be adding 12.36% interest. The other one is going to be 1% interest. So that is a growth factor of 1.01. The first one maintaining the current amount, and the 0.01 representing the 1% interest. And my exponent is going to be 12 because we're applying it every month. When we put this into a calculator, 1.01 to the power of 12, if we round to the same 4 decimals, this is 1.1268. That means it's charging 12.68% actual annual interest. So the answer is no, they don't pay the same amount of interest. The 1% applied every month would actually pay slightly more than the 6% paid twice a year. If you have any questions about how to solve this practice problem, please leave a comment below and I'll get back to you with any help I can offer. Our next practice problem says a bank pays 8% nominal annual interest rate, compounded at the end of each month. An account starts with $600 and no further withdrawals or deposits are made. Number 1, what is the monthly interest rate? So if we want to take the monthly interest rate, we're going to take the nominal interest rate, which is 8%, and we're going to divide that by 12 months. So this becomes 8 divided by 12, which is about 0.67%. Number 2. Write an expression for the account balance in dollars after 1 year. So, we're going to start with $600. And we're going to multiply that by the growth factor. We have 1, which maintains the current amount, plus I'm going to take this 8% and I'm going to turn that into a decimal, 0.08. And we're going to divide that by 12. Now, the reason that I'm writing it this way is because when I said it was 0.67%, I was rounding it to 2 decimal places. So to ensure that I don't round in the future until I get to the final answer, I'm going to write it as the fraction so that I put it in the calculator and I do all my calculations without rounding, and then I will round when I get to the final answer. And then, because we are doing this for 1 year, and because this is monthly, my exponent is going to be 12, because I'm going to apply this interest 12 times. Number 3, what is the effective annual interest rate? And by effective, they mean the actual annual interest rate. So we're going to take our growth factor to the power of 12. So that's 1 plus 0.08 divided by 12 to the power of 12. And when we put this into a calculator, we're going to get 0.08 divided by 12 plus 1 And now we're going to take that to the power of 12. And here we get 1.082999. So I'm going to round it to 1.083. So the 1 represents maintaining the current amount. The 0.083 equals 8.3% effective annual interest. So even though the bank advertises that they pay an 8% nominal interest rate, they're effectively paying 8.3% in reality. And number 4, write an expression for the account balance in dollars after T years. Well, the only thing we need to change from number 2 is that instead of the exponent being 12, 12 represented 12 months in 1 year. So if we just multiply those 12 months by T, then you could substitute in any number of years, multiply those number of years by 12, and that would tell you how many monthly interest installments to apply. So we have our $600 starting value times 1 to maintain the current amount plus 0.08 divided by 12. That takes the 8% nominal rate and divides it over the 12 months. And then your exponent is going to be 12 months times T, the number of years. If you have any questions about how to solve any of the practice problems we've gone over, please leave a comment below and I will get back to you with any information I can offer. Before we end this lesson, let's go back and take a look at the learning targets and make sure that you're set up for success moving forward into future lessons. As we finish up, I will just want to look at these learning targets one more time. Number 1 says I can calculate interest when I know the starting balance, the interest rate, and the compounding intervals. So remember, if you're talking about a nominal annual interest rate, you need to divide it by how many times you're compounding it in the year, and then your exponent is going to be the total number of times that you're compounding it. And learning target number 2, when given interest rates and compounding intervals, I can choose the better investment option. So just remember, don't get fooled into thinking that a higher interest rate means a larger payout. You need to know how many times in a year that interest is being compounded, And then you need to actually calculate which one has the better return on investment. If you feel comfortable making both of these statements, then you are prepared to move forward into the next lesson. If you still have any questions about this lesson, please leave a comment below and I'll get back to you with any help that I can offer. Thank you for your time. I ask that you hit the subscribe button, give this video a thumbs up, leave a comment if there's anything I can help you with, and I look forward to seeing you in the next lesson.